Yeah,
Okay.
yes.
Good evening, one and all. IEEE Malabar Subsection, in association with IEEE Malabar Hub, is hosting a weekly webinar series on every Thursday at 5:30 p.m. And this event was started from June 2020, during which we had a lockdown. And the aim of this event is to share the knowledge among the IEEE as well as non-IEEE community. And till now, we have completed 61 webinars, and this is our 62nd webinar. And today, we are hosting this event jointly with IIT Palakkad. And today we have eminent speaker from IIT Palakkad itself, Dr. Mahesh R Panicker. And he'll be talking on the topic Diagnostic Ultrasound, the journey from imaging to therapy and beyond. And before getting into this topic, I'll have a short introduction about the speaker to the August audience. Dr. Mahesh R Panicker received his BTech degree in Electrical and Electronics Engineering from Rajiv Gandhi Institute of Technology, RIT, Kottayam, in 2003 with first rank in university, and PhD degree from School of Computer Engineering, Nanyang Technological University, NTU, Singapore in 2009. From August 2003 to July 2005, he was a lecturer with Mahatma Gandhi University, Kerala. From August 2008 to July 2010, he was a postdoctoral fellow with Center for High Performance Embedded System, NTU, Singapore. In August 2010, he started his career in industry with General Electric Global Research Center, Bangalore. He was a lead research engineer with GE till April 2017. From May 2017 till May 2018, he was Senior Chief Engineer with Samsung Research Institute, Bangalore. Mahesh is a senior member with IEEE, Six Sigma Green Belt certified, and a TRIZ practitioner. He is a recipient of the prestigious Early Career Research Award from Science and Engineering Research Board, Government of India in 2019. He has won GE-wide Technical Excellence Awards in 2013 and 2015. He has also won Silver Award for 10 or more patents with GE. During his stay in GE, Mahesh has worked on a range of projects which include portable fetal ECG platform, compressor blade health monitoring program, real-time detection of rotor imbalance in GE transportation locomotive engines, detection of corrosion under insulation in oil gas pipeline in refineries, nuclear reactors, etc. Mahesh's research interests include signal processing and analytics, reconfigurable computing, and area-efficient low-power system with applications in diagnostic ultrasound imaging, biomedical circuits and system, multi-strand wireless communication, and industrial prognostics and health monitoring. Mahesh has published his research findings in 10 international journals, 37 conferences, and 10 patents. With a huge welcome. We are from IEEE Malabar Subsection. I welcome you, sir, to this webinar series. Hope you will be enlightening this session.
Yeah,
Welcome you, sir. Over to you,
thank
sir.
you. Yeah, thank you, Sabik. So I hope all of you can see my screen. And first of all, let me congratulate the organizers because this is webinar number 62. So that means over the last 1 year or so, we had so many of them. And that's given the situation that we are in, I think this is the best way to keep our learning going. And in that sense, the organizers definitely should be proud of it. And we are also part of IEEE Malabar section. So this definitely we'll be happy to be part of it in the longer journey as well. And thanks to Hari and IIT Palakkad IEEE team also for taking initiative in this direction. And first of all, thanks to all of you who are joining this session. And without any further delay, let me just introduce the topic for today's discussion. And I'm sure some of you are familiar with ultrasound. I can see some of you already here who are working with me as well. But majority of you, I think, not sure about what is the talk about or what is he going to talk about and all those things. So initial part of the talk, we will try to cover the very basics, the physics and all those things. And then later on, we will go to the advanced stuff where as an engineer, you will be able to contribute in this journey. Okay, so I have been in this field for almost like 6 years. Started with GE, continued with Samsung, and last 3 years in IIT Palakkad. Also, we are building a team. But this talk doesn't cover any of the work that we are doing, but rather the very basic stuff and the generic stuff. And maybe at a later opportunity, we can talk about the work that specifically we are doing. Okay, so what is ultrasound imaging, or what is ultrasound to start with, right? I mean, many of you, the irony is that we have studied about electromagnetics, electromagnetic waves, electromagnetic spectrum in detail in your undergraduate, right? Whether you're electrical or electronics, doesn't matter. You might have studied that. But unfortunately, the sound that we see or what we produce and what we listen day to day is not actually given priority in our undergraduate studies, which is strange rather. And to start with, ultrasound, or for that matter, sound, is a mechanical wave. It's not an electromagnetic wave. So there's a huge difference, because electromagnetic wave can propagate. It doesn't need a medium to propagate. It can go in vacuum as well. But sound is a mechanical wave, so it needs a medium to propagate. You can see a demo here, and something which is producing a vibration, and it utilizes the particles in the medium to propagate. So if you observe carefully here, the red dot here, that is a particle in the medium. It is really not moving from left to right, but it is actually in fact moving from left to right, but around an equilibrium position, right? But on the other hand, the disturbance, the wave that I'm creating at this stage is actually getting transmitted from this position to this position all the way, and it uses the particle or the medium along its path, right? So it uses the material property of the medium for the propagation, and that actually makes ultrasound imaging unique, because through ultrasound imaging you will get the structures in the medium that you're scanning. Beyond that, you can even get the properties of the medium that you're scanning. So that's where actually the modern day ultrasound technologies are going towards, which we'll discuss as we go along. But in terms of the disturbance frequency, it is somewhere above 20 kilohertz, because below 20 kilohertz is we consider as audible sound. So above 20 kilohertz up to 1 gigahertz is the typical range of ultrasound frequencies. But diagnostic ultrasound, if you come to, when we say diagnostics, which is used for healthcare or medical, that is restricted to somewhere between 1 megahertz and 50 megahertz as of we speak now. Okay. And then ultrasound imaging is popular. If you're not heard about it, it is popular because, or it is going to be more popular in the coming few days, because it is cost effective. It's really, really low cost. It is portable. You can take it to the bedside of the patient, unlike compared to a CT or an MRI machine, which is otherwise used in imaging, right? You can take it to the bedside. Dynamic imaging is something which is interesting, because most of the time you might have at least taken an X-ray scan in your life, right? And the technician might have asked you to be stand still when the X-ray is taken. You cannot move. So it's like you have to be static. But on the other hand, ultrasound is not like that. You are free to move when the scanning is done. So that's why it becomes important in many modalities or many organs that you want to scan, dynamic imaging. And then it is not ionizing, because it is just sound, the sound that we experience every day. You are also exposed to ultrasound day to day, but we are not hearing that because it's not in our audible range. So it's not ionizing. It is there everywhere. And if you apply it at the right energy, then it's not harmful at all. Okay, so that's the important aspect. And it is applied a lot, particularly in OBGYN and cardiology. So for example, neonatal and fetal scanning, there is no other modality. You can't apply MR or CT or X-ray there because of the ionizing radiations and magnetic effect. So only modality which can be applied so far is ultrasound. And you might have seen that also. Ultrasound scanning in fetal is a lot popular. Cardiology also is a similar scenario. Okay, and it is getting popular in neuroimaging, pulmonology, vascular imaging, musculoskeletal, all the organs that you can think of. It is getting popular in the recent times. So all these are generic stuff, just introduction. But as an engineer, we will be introduced in how an ultrasound can be produced and how it can be used for imaging. Okay, the medium under observation or the organ under observation. The technology is very simple. Okay, sorry. So the idea here is actually you will have an array of transducers placed in the shape of a convex or a linear array, and then they will transmit some waveform into the body. And wherever there is sort of material difference, you will get some reflections back, and that will be captured by the same set of transducers. And then we will create an image, something like this. Okay, so you might not have seen this sort of an image, but it actually shows baby inside mother's abdomen. Okay, so we'll talk about the details of how the image is produced and what is the exact engineering behind it in the next few slides. But before going into any technology details, most of the time it will be, we are always curious to know the technology evolution, right? So here I would like to show you where it all started. So way back in 1880, the Curie brothers discovered the piezoelectric effect, which is nothing but if you apply electricity onto a certain material, it will produce vibrations in the form of sound. And if sound falls onto the same material, it can produce electricity back. So that's a piezoelectric effect, right? And it's reversible. In 1950s, a group of Australian scientists, so this is actually taken from Australian clinician named John J. Weil, but at the same time, the same effort has been happening around the world. So just a pictorial representation. But around 1950s is where the thought process came that the sound can be used to image body structures and organs which are inside the body. So here, for example, it's quite fascinating to see it. So a person is sort of immersed in a water tank, and you have a transmitter and a receiver which will sort of rotate around his body and create the entire structure and entire internal structure of the body. So this is 1950s. And where are we now? Okay, so this is somewhere around 2000 where such fascinating engineering marvel actually came into existence. So when we talk about engineering marvel, we talk about television, mobile phones, all those things, right? But people never hardly talk about the beautiful machines in healthcare, something like an MRI machine or a CT machine or an ultrasound machine. There's actually a lot of engineering behind it. And unfortunately, we don't spend a lot of interest or a lot of stress on these aspects. So here, for example, there's a lot of processing happening right here. The CPU is here, and then you have the interface here and the display here. So it's really beautiful to see. We'll discuss about the engineering behind it in detail in the next few slides. And where are we now? As of we speak, 2021, all the Moore's law, all the miniaturization in electronics has helped us to shrink everything a size of this to a size of this, which is like you can hold it in your palm. So this is what I was talking about, the portability earlier. Okay, so here, for example, this is the typical probe. So you have the arrangement of transducers here on both sides in the shape of a convex array here and a linear array here. So both sides can be used for scanning. And then the whatever information scanned is sent to this particular mobile system, which is basically a Samsung S3 or an Apple iPhone. And you can see the structure, the human structure inside on this screen. So it's so flexible. Okay, so this is a wireless system which is introduced by GE in early 2021. Now, let's go into the details. All those were generic stuff and just gradual introduction to this. Now, let's talk about the physics part and then the engineering part. So what is ultrasound imaging physics? So as I said, array of transducers, it will produce some sound wave and that will be passed on to the body. And what happens actually when the wave will propagate through the body or the tissue or the medium, and some part will get scattered. That means it will get reflected in all directions, and some portion will come back to the transducer, and we will use it for imaging. Since it is scattering, that means the energy received at the probe or the transducer will be very minimal. And if you see from an image perspective, this will be like not a very large intensity structure. It will be something which is somewhere in the middle of the grayscale. Okay, so that's what happens. Another interesting fact is like some of these materials inside the body will sort of completely reflect the wave back to the probe. Okay, so this we typically call as reflection per se. The other one we call it as scattering. And we will discuss in more detail in the subsequent slides how can you say that it is going to be scattered or how it is going to be reflected. So that will be discussed in the subsequent slides. But all you can think of, I'm sending some wave, some of them will get scattered, some of them will get reflected back. an example of such a structure is a bone in our body. It will reflect the sound completely back. And then if something is remaining, it will get absorbed also in such tissues. And how absorption happens, you can think like, because when we talk about ultrasound, it is a mechanical wave. Mechanical wave means you are actually creating motion in the particles in the medium or the material. These particles will have a lot of random motion. They may clash each other, and some of them will get dissipated as heat. So that's exactly what we are talking about here. Some of them get absorbed in the form of heat. And you will think that it's a waste. No, that is where actually people are so clever. They're using this loss also to the advantage, which we will talk in this lecture. Okay, beyond imaging, therapy side, a lot of application comes from this property of absorption. And whatever remaining, you scattered, you reflected, you absorb, whatever remaining will continue its journey and will get again, maybe any of these will come back. So it just goes on, and whatever we observe here, this entire space, this entire thing will get imaged. Okay, so that's the whole idea. Okay, so let me remove it. Yeah. Now, how these things will happen, scattering, reflection, absorption, how these things will happen, it purely, as I said, it purely depends upon the material property. So just for the sake of understanding, I just list down the density and speed of sound, which are two of the important material parameters which is affecting the reflection. And these two, when multiplied together, we term it as acoustic impedance, in analogous to the impedance of an electric current. So similar to that. So more the acoustic impedance, more resistance will be offered for the propagation of sound. Okay, less resistance or less impedance means you will be moving faster. So that's the concept. And you can see over here, air offers the least impedance. So then you will think that, oh, then I can use air. It will just pass the ultrasound very fast. But you see the second property here, absorption. Okay, so this absorption actually is a serious issue, because the more the absorption, that means it will get absorbed there itself. It will not propagate further. So that means air will actually least impedance it will offer, but it absorbs a lot. And interestingly, this is measured in dB per centimeter per megahertz. So it's natural to think that larger the depth, absorption will be naturally be higher. Okay, so when it's quite evident, right, for us. As the distance is increasing, depth is increasing, it gets attenuated or absorbed more. So the energy will be propagated less. And similarly, frequency, higher the frequency, the absorption will be more. So that's these two I just want to mention here, because I'll have some examples in the coming slides. So it's very important. So you think that air is good medium, but no, the air actually absorbs a lot. And that is the reason, if you observe the first slide where I showed you 1950s, the person was sitting in the water tank. The reason why it is not an air tank or just sitting outside, because air attenuates it heavily and you really can't image the body. So you need to have a medium like water, which is similar to blood, you could say. The attenuation is not that high. So it sort of efficiently allows the sound to get transmitted, reaches the body, gets reflections and image it. So that's the reason why we really don't, I mean, there is a trouble when we have air. Another instance I could actually take you, if you have done ultrasound scan, you might have seen that the doctor's putting the gel on the surface of the probe. So that the reason is to avoid the air gap in between the probe and the body. So if you apply gel, it nicely couples the sound from the probe to the body. There's no loss, or the loss is very minimal. And similarly, if you have gone for abdominal scan, or if you may go in future for an abdominal ultrasound scan, doctor will ask you to drink a lot of water, because typically our abdomen will be having a lot of gas, and that will not allow ultrasound to penetrate. So if you drink water, you will have that medium enabled to have sound propagation. So all this you can even see in the previous image that I was showing you. The top is like the muscle, the fat, all those reflections are shown here. And the amniotic fluid, which is inside our mother's abdomen, that will not reflect the sound at all. That's why you see it completely dark. And then if you see over here, the skull, the nasal bone will look like a reflector, and that borderline you can see also very clearly. So now some more details I'll quickly go through in these slides. Some more details about these phenomena, particularly the reflection, scattering, and the absorption. I will just quickly show you with some demos. So when will the reflection happen? We call it a specular reflection commonly. and there is a refraction also associated with it. That means the transmission is going to change a bit based on the reflection. So that's the meaning of refraction. So I'll tell you an example. Examples of these are bonds, needle, all those things which are rigid structures, and most of the time they will be having a depth or a width which is much higher than the wavelength of the sound wave that we are transmitting. If that is going to happen, then what is interesting is complete reflection will happen. Okay, so just an illustration here. You have two mediums, a top medium with some speed of sound C1 and a bottom medium with some speed of sound C2, and the depth of this medium is larger than the wavelength of transmission. Okay, so if that is going to happen, then interestingly the incident wave which goes like this hits the interface. So there is a sort of impedance change from this medium to this medium, but then this medium is having the depth much higher. What is going to happen is the wave will get reflected almost completely back at a certain angle. That angle can be determined by Snell's law. You might have seen this in your +2 or 8th standard physics, where we discuss this from the light perspective, right? We might have talked about light getting this refraction issues, and when you insert let's say as some material into water, it looks like the material has bent, some bent which was not naturally there, right? The same phenomena. So we can easily determine the reflection angle from the knowledge of the incidence angle, and then the wave, whatever remaining, will not go in the same. If ideally speaking, this would have gone like a straight line, right? Like this, but it will not go that way. There will be a slight bend, and that is because of this particular property of the material. And because of that, we will have a refraction effect. And I have a simulation here actually developed by Gayatri, one of my PhD student. I think she's also attending the talk here. So she has nicely simulated this phenomena. So you will see a wave which is propagating straight down and or at an angle. And then as it hits a specular reflector here, it changes its direction completely. So a direction is incident here and it goes like this. Similarly here, it was incident like this, it goes like this. So the wave changed its direction, or the entire thing is sort of reflected back. Most of the energy is reflected back. And that's very, very important, because if we don't understand all this, the engineering system that you design at a later point will suffer. An example is here. So this is a needle which is getting inserted into a vessel. So this is a blood vessel you are seeing over here. So in this video, you will see a needle getting inserted. And you will see that some portion of the needle is not very clear. The needle is not really visible. The reason is because my imaging system is not really developed well. It is developed for a scattering sort of scenario, but not for a reflection sort of scenario. So you see that needle is not at all visible here. That is because the reflections are going in a certain direction, and I have not done the system in such a way that it receives those correctly. And also, if you observe carefully, the part of needle here and here is not exactly in a straight line. There is a slight bend. That is because of this refraction property. Now, this is about reflection. And I also talked about the scattering part. We call it also as diffuse reflection. That means the wave will get incident and it gets scattered in all directions. Again, I will show the simulation. The same wave, but here it's a small scatterer. So you can see the reflection now. It is actually going in all directions. It is not really coming in a particular direction. It is just scattering all throughout. And some portion will come to the probe as well. So the takeaway from here is, like, if we have a specular reflector in the medium, it will reflect the waveform in a certain direction with high intensity. If you have a diffuse reflector, it just scatters it throughout. And that's the reason why if you see an ultrasound image, you will see a lot of small textures. We call it as speckles. That is because it is scattered in all directions. And you will see some heavy structures which are sort of in that, for example, in the case of that image I shown, the bone which gets sort of high intensity in the image. Here also, I will show an example. So this is the third aspect. So we talked about the reflection, the scattering, and now the third aspect was the absorption. And I also told this is due to the random motion of the particles. Now, if you see the two cases are shown, these images, if you are curious, this is taken from musculoskeletal. This is our shoulder tendon actually imaged here. And this is taken at a frequency, let's call it as a fundamental frequency, and this is taken at a frequency which is twice this frequency. So if you remember the table I was showing you, there it was clearly mentioned that the absorption will increase with frequency. And you can actually see between these two images, you see these sort of structures which is disappeared from here. It's not an artifact. It is because this is at a higher frequency. So it gets attenuated. It gets absorbed faster than this particular case. So that's immediately you can see. Another important thing, which is really not part of the discussion, but I thought I'll tell you that also. This image doesn't look as high resolution as compared to this image. This image is actually looking better, right? I mean, in terms of resolution. The reason is because the frequency is twice compared to this frequency. So that means higher the frequency, lower the wavelength, and resolution will be obviously better, right? Because lower wavelength means you are able to distinguish between particles which are closer. So your resolution is going to improve. Okay, so with that, let's go to the engineering details. I'll have to maybe speed up because I need to talk about the advanced part also. So the engineering system may look like this, an expensive system, or it may look like something like this. So can somebody guess the cost of this system? You'll be surprised that this system, whatever you're seeing over here, which is developed by Butterfly Network, it is just costing $2,000. That means the cost is lower than an Apple machine. So that's the stage that we are at. Okay. So what are the essential engineering components now? So we talked about the physics. We had a brief introduction about the scattering, all the medium aspects. Now let's talk about the engineering aspect. Okay. And let's spend some time also in this. So the most important aspect is the probe, right? I need to generate the ultrasound. So the traditional technology, let me again zoom in here so that you don't lose out on the other aspects. So the conventional effect is the piezoelectric effect. And you already have a wide variety of ways you can arrange the transducer. It can be arranged in a convex shape, a linear shape, or different shape. And you will be wondering, where are these different shapes used? So different shapes have different applications. For example, if you're going for an abdominal scan, I need to have a wide field of view. So then obviously you will choose something like this, right? Because you can get a wide field of view because of that shape. If you're going for, let's say, something like a musculoskeletal where the depth is not very large and I just want to focus superficially, you'll go something like a linear array of transducers. So it's purely application dependent. But what is inside? So the inside architecture is something like this. You will have arrangement of transducers like this. Okay. And each of them will be excited with some frequency, and all of them will produce sound, and all of them will go together as a wave in front of the into the medium which is in front of the probe. And you don't want all those waveform to go back or in some other directions, right? Everything you want, because you want to image only what is right in front of me. I don't want something going behind or something going up and down. So to ensure that, so what engineering technology what we use, we'll have backing layer. I think similar to the antenna technology that you can think of. We'll put a backing layer at the end or behind the transducer so that nothing goes back. And similarly, we'll put an acoustic lens to ensure that the waveform will not go up and down. It gets confined to a plane which is directly in front of the probe. So this way we'll ensure that everything, whatever we want to look at, is right in front of me. I should not look at back. I should not look up and down. It should be right in front of me. So that's the way engineers designed this. Okay. And the modern day technology, so this is the traditional one. The modern day technology is, as usual, the miniaturization. So a lot of MEMS being applied here. This is piezoelectric effect is a beautiful conversion of electrical energy to mechanical energy, right? So obviously MEMS has a dominant role here. So people have discovered something known as CMUT. So capacitance micro machined ultrasound technology is the expansion for that. So it is purely electrical technology, which sort of mimics the mechanical effect and produces sound. And those who are interested in the substrate fabrication, how does it look like? It is this. And what it does actually is the cost of the probe has come down drastically. And that is why people are able to bring down the cost to something like $2,000 that I was talking about. Okay, so we talked about the probe. This is what needed to trigger that sound into the body. But then of course you need a backend, right? You need to have electric supply to this, and that's where the analog processing is important. And the more important aspect, maybe I missed to mention, the same set of transducers, because piezoelectric effect is used for transmission of sound as well as reception of sound. I think I missed it. Sorry for that. So that's very important. So that means our analog front end should have the provision to switch between transmit path, which is the top path, and the receive path, which is the bottom path. So there is a transmit receive switch here. And of course, as I said, we need to apply the voltage at the right frequency. So we have a high voltage pulsar, which is sitting right here, which will get to each and every transducer here, and that provides a signal. And then of course, we need to control all this, right? That's very important, right? We need to control the frequency. We need to control the depth, how much depth I want to scan, all those things you want to control. So that happens at the back end, or we can call it as digital front end. Okay, this is a combination of FPGAs, ASICs, GPUs. So, and if you think the top part, there's a beam. So this is the major engineering aspect here. So the technology that drives the ultrasound according to what you want, according to where you want the wave to go, that is known as beamforming. Okay, so this terminology you might have heard, those who are working in communication might have heard this terminology of beamforming. It is exactly the same. The only difference between there and here is here we are using it for imaging, there you are using it for communication purposes. So that's the only difference. Otherwise, the terminology, the ideology, everything is same. So the heart of any ultrasound system is a technology known as beamforming, and we will focus maybe 5 to 10 minutes exclusively on that. There are two types of beamforming happening in an ultrasound system. One is the transmit beamforming, and the other one is the receive beamforming. And in fact, receive beamforming is the technology which takes the data from each and every transducer and converts that to an image which that we see on the machine. Okay, because each and every transducer will pick up the signal, right? You need to convert that to an image so that you can see some structure in front of me. So that's exactly happening in the receive beamforming. Now let's talk more about this part, which is the heart of any ultrasound system, beamforming. Okay, so we'll start with ultrasound beamforming. First of all, the transmit beamforming, and this picture actually sums it out. Okay, so a picture says sort of everything what I want to convey, right? So you have the array of transducers here. You can even think of something like an antenna array, exactly same principle. So if I, let's say, delay, I give the same signal to each and every transducer, but only thing that I'm going to play, a trick I'm going to play is basically delay the signal in each of these transducers. That means I will not give the signal at the same time to all the transducers. I will delay it. If I delay something like first this transducer is given the signal, then this transducer, do that, the wave will go in certain direction. So beamforming, the transmit beamforming specifically will give directivity to the wave that I want to propagate. So how the material behaves is shown here, and how the wave is generated is shown here. And this is what typically you see in a communication system. But in the case of an ultrasound system, we will go one step beyond this. We can, directivity is one aspect of it. The second aspect is using beamforming, I will be able to actually focus all my ultrasound energy to a point that I choose. I can decide the focal point in front of me. Let's say I want to focus at 2 centimeters. I can do that. So how to go about it is explained here. So this is the transmit beamformer. So there is some signal processing circuitry, digital circuitry sitting here that will send the signals to each and every transducer. So let's assume here 9 transducers sitting in a linear array. So that's what showing over here. Now let's say you want to focus at a point in front of it. Let's say the imaginary coordinates of that particular point is xf, zf, xf standing for the x coordinate, zf standing for the z coordinate. So this is the focal point I want to focus my ultrasound energy in. So those who are not understanding this, just think of something like I want to send the waveform from each transducer, but if I measure the energy of that waveform in this space, in this larger space in front of me, so let's say this is the space I want to image. So in this larger space, if I consider so many pixels around, if I measure the energy at all these pixels, you will see that the energy will be maximum at this point. So that's the thing I want to achieve through transmit focusing. So how to go about it? So I already told sort of approximately what shall we do towards that. So very trivial. This is not really an engineering. This is some 8th standard trigonometry that we studied. You want to ensure that the energy or the amplitude of everything when summed up together should be maximum at this point. The way to go about it, you find the distance between this particular point to each and every transducer. So let's say this XF ZF with this transducer. Find this distance. What is that? Very simple, right? This is a formula. So let's assume that Xi and Zi are the senders of each of these transducers. XF ZF is the pixel locations, coordinates. Then the distance between the transducer to the pixel is nothing but this formula which we studied long back in 8th standard, right? Xi minus xf square plus zi minus zf square. So this gives me the distance. So I can vary for each and every transducer. So based on the respective transducer, you will get a distance. Obviously, this distance will be larger compared to this distance. That's pretty clear to us, right? And then when we have the distance, if I divide by the speed, assume some speed of sound, and if I divide by that speed, we already had a table earlier with the speed of sound, some approximation. Then I get the time that the wave will take from going from this transducer to this transducer. So the idea is very simple. My objective is to focus at this point. So first step is find the distance of this point from each and every transducer. Moment you find the distance, you can find the time. And if you find the time, I will transmit the signal in such a way that based on the time, I will delay some signal and I will advance some signal in such a way that everything will propagate. As it propagates, when it reaches at this point, everything will be aligned in time. For example, in this case, this is transmitted first, these two. This is transmitted last. So what is going to happen is this guy will transmit, it comes, and then this guy will come. But then the distance of this guy to this is shorter. So everything will come at this point at the same time. So if you're not convinced here, I'll have an example here. It's a simulated example. So let's say I want, so the axis here, the depth axis is depth. I mean, sorry, the y-axis here is the depth. The x-axis here is nothing but this dimension. Okay, so you can see over here some 16 transducer row signals are shown over here, and this is basically the sum of all these. Okay, so if I sum in this direction, this particular direction, I get this signal out. So if you see, so here what I did is actually I focused at 1 centimeter. Okay, so you can see over here they're all aligned at 1 centimeter nicely. If I go at another depth, you can see it's not aligned at all. So that's why if I add up, you won't get the same energy at all positions. So you can control. So all you need to do is basically just control the delay so that you decide where you want to focus. So this is known as, so this is another case, 3 centimeter focus. You can see they are all aligned at 3 centimeter, not at all aligned at 1 centimeter, but perfectly aligned at 3 centimeter because we are delaying the signal in such a way. Okay, so it's very important. It's we controlling. It's not naturally happening. We are controlling it. And that's what known as transmit beamforming. This is another case where the focus is at 5 centimeter. You can see here it's not at all aligned. And then as the depth increases, it automatically, because we delayed it accordingly. So this is transmit beamforming, the same concept. Yeah, before going to the receive beamforming, I just want to highlight. So what is the significance of this? This is what we call as focus transmission, where literally I can control the energy at a certain spot in front of me. I can ensure that ultrasound is reaching there with maximum intensity. This is extremely important because this is what some of the modern day concepts are purely based on. Okay. Now, this also gives me directivity, right? We saw that I can actually, this is one example. I can put the focal point anywhere in space. Let's say here, I can focus here. I can focus here. All we need to change is that equation, the values will change, the distance will change, the time delay will change, and you can focus here. So it doesn't matter where is the point in space. You can literally focus any point in space with precise control. So that's what transmit beamforming is all about. But then irony is that the problem is, let's say I want to get a good image. I want to focus at all points, something like this, along this particular horizontal line. So all these red dots I put is the points I want to focus on to create a good quality image. But then the problem is it takes some time to focus at this point, then again at this point, again at this point. So your frame rate will be low. So when I say frame rate is like, imagine you're transmitting the waveform, then everything will go to the receive mode. So you'll receive the signal, you reconstruct the image, then you go to the next, right? So you'll again sort of transmit the signal, then receive the signal. So your frame rate is going to suffer for focus transmission. So people are moved on and sort of move to something known as unfocused transmission or plane wave transmission. If you're coming from antenna theory, you'll know that. So in that case, there's no directivity, there is no high energy content, but you will achieve high frame rate. So many of the modern day techniques are purely based on this concept. Okay. So now we talked about transmit beamforming. The same concept can be reversed in the case of receive beamforming. So just the opposite. So I don't spend much time here. So let's say from this point, so you can imagine any point in space. We'll just assume this is one of those points. You get signals from this point, but we know that the distance from this point to the transducers are different. So they will not come at the same time. This guy is the shortest distance. So I will receive that first, then only I'll get receive signals from this. So when I reconstruct the signal, when I reconstruct an image from the signal, reconstruct this particular pixel, I don't add them up as it is. But what I do is actually based on this distance, same formula that we used in the previous slide. And based on that, I will first, same formula, nothing difference, except we'll add a small extra delay. This is nothing but the transmit delay that you're applying. If you're going for a focus transmission, you already might have applied some delay, right? So you need to compensate for that delay. If you're not going for any focus, you don't need this. You can just go for this standard expression. So only change from the previous slide to this slide is the variable change. In the previous case, it was F. Now it is K. That's all. Remaining everything is same. So using this formula, you identify the distance and the delay, and you need to compensate for that particular delay what you have here. So you compensate it, everything is aligned in phase. Now you can actually sum them up together, which we call as beamforming usually. And then you repeat this process. This is for one pixel. You repeat this process for each and every pixel in this space. So you take another pixel, another pixel, another pixel. You repeat this process and finally stitch everything together. You will get an image out. Of course, I'm skipping a lot of small processes in between because this is a very generic lecture. I don't want to go into all the details, but this is the holistic picture that I can give you. So transmit beamforming is separate, receive beamforming is separate, but fundamentally the concept is same. Only thing that you are going to do is, given a pixel, you identify the distance from that pixel to the transducer array, compensate for that delay, and then you add them up together. You get the signal out from that pixel, and you repeat that process for all the pixels, stitch them together, you get the image. And one important thing I just want to focus here is, you might naturally think that, let's say this transducer is having the shortest distance from this pixel. So it will be receiving the highest energy, right? Because as the distance increases, attenuation increases. So this transducer may not get the same energy as this transducer. So instead of just simply adding them together, you can even weight them according to the distance, for example. That is why in this formula, I'm not going to this formula. You can weight each of these signals according to the distance, let's say, and then sum it up. People call it as apodization, and the same terminology that digital camera uses, we call it as aperture there. The same concept can be employed here also to improve the image quality. Okay, so we talked about transmit beamforming, we talked about receive beamforming. Now we'll again go back to something which is generic. So hope you understood the basic, the heart of an ultrasound system, what can be done to improve the image quality, how is reconstruction done in a very, very top level. Of course, that's only what we can achieve this with this sort of a session. Now, ultrasound can be used for different ways to image an organ. So very, very trivial way is something like single signal, okay, single transducer. So it's something like this. You have a single transducer, it emits a wave, it gets back the wave, and you plot it on an oscilloscope. It is just a signal level, nothing much, no image here. It's just amplitude plot. So that's why we call it as A mode. But if, as we discussed so far, so I don't go into details, I can create an image by reconstructing from each and every pixel using that receive beamforming technology. I can create an image out of it. Okay, so here, for example, this is an image of a baby, and you got two small sort of dark regions that you see over here are the two chambers of the fetal heart. Okay, the reason why I want to emphasize that is I can do something more than just the image. Imagine I am going to create multiple of these images by continuously transmitting the ultrasound and reconstructing the images. So one frame, next frame, second frame, third frame, fourth frame, etc. And I'm going to observe this particular column. Okay, in the image, just observe this column across the frames. If I do that, it is known as M mode. Okay, motion mode. So just this particular column of the image, if I observe over the frames, you will see something like this. So what is so fancy about is what you see over this variation is the fetal heartbeat. Imagine it is way inside mother's abdomen at a depth of maybe more than 10 centimeter inside the abdomen. You are using non-invasively, you're pumping in sound and you're getting a B mode structure. Not only that, if I consider only one line of that image and across the frames, if I plot, I will be able to get the fetal heart rate. I didn't disturb the baby. I didn't disturb the mother. I can get the fetal heart rate of a baby who's right inside mother's abdomen. That is why ultrasound is so popular in OBGYN technology. Let's speed up a bit. Ultrasound can also be used. Now you might have got, okay, I can get the structure. I can get the functions also. One example is here. Another example is Doppler. I can keep on pumping in the transmit at a specific pixel. And if I see that pixel is moving, what is going to effectively see is if I consider the phase of that signal at that pixel at time t1 and time t2, if I see the phase shift of the signal, I can get the basically the velocity magnitude at that pixel. This is very useful to track. This is, for example, the heart, and the color actually shows the intensity of the blood flow. The red actually shows higher velocity, and the blue actually shows lower velocity in this case. So this is what the current commercial system is all about. So if you go to hospital and you get a scan, you will be either going for B mode, M mode, or Doppler mode. So this is what so far what we have. Now next few slides is going to be about the advancements in this field. And one such advancement is going from a simple Doppler mode to identifying something like a velocity at that point. So earlier plot I showed you is just giving you the magnitude of the velocity blood flow. Either it is high value or low value or some magnitude. But imagine you can visualize the blood flow inside your vessel. You can actually sort of, idea is very simple. Due to lack of time, I'm not going to tell the exact details. It is just like you observe the blood flow from two different positions, and then you can actually do something known as triangulation to identify the horizontal and vertical components of the velocity. So some work we are doing in this field. So if you're curious, you can always check our webpage. Madhavan is there in the call. He's sort of doing a lot of interesting stuff in this field of displaying something like this. So you have, this is actually from a reference which is right over here. So what we are seeing over here is the carotid, which is somewhere here, which nicely separates the blood flow to the brain. So if you track it nicely, what we can identify is an onset of a stroke. So this is a classic example. So there is some plaque deposit which is happening here. And because of that, the blood is not really going smoothly. It's creating some vortex flow, which is right over here. And that is an onset of something which is very serious in the human body. Okay, so this is very important. And this is something which is going to revolutionize the ultrasound imaging in the coming. Many teams are working in this, and we will see that this is going to be commercialized in the very recent time. Let's move on. And now other things that we can do. We already know that ultrasound nicely captures the material properties. So why don't we use it for something known as elastography? We know that when there is cancerous tissue in our body, that will get more stiffer, and stiffness increase, it doesn't vibrate that well, right? So can I induce some manual vibrations in the body and then use that high frame rate approach or multiple frames approach to sort of distinguish between a stiff tissue and a non-stiff tissue? So this is from a team in IIT Madras, Professor Arun Tittai's team. So very interesting work. So here what they're doing is they're pushing the probe and inducing sort of vibration into the tissue. And wherever there is stiff tissue, it will actually sort of vibrate more compared to the surrounding tissue. And you can actually, the red color, so if I take multiple frames and do a correlation between the frames, I can calculate the displacement. And if there is huge displacement, it will be shown as red, and others will be shown as blue. And this is very trivial. What they did is one step further. They put a motor, something like a vibrator, which we use in mobile phone, right? That motor here. And instead of this irregular hand motion, they put a motorized motion into the body that will induce some vibration in the tissue. And again, going by the high frame rate correlation between frames, you will be able to. So you can see the difference. So this is not very good, but still it is able to identify that there is a stiff tissue here. But this is very, very clear. You have a circular stiff tissue here. And imagine this is already being applied for breast cancer detection. and it is a commercial product which is just getting FDA approved. So maybe it will come in near future. And you thought this is the end of it? No, not really. I induced manual motion, I induced motorized motion. Somebody should always think that ultrasound itself can create vibration, right? Because it uses the medium to propagate. So people have done that also. So you can use ultrasound itself to create at specific spot. You imagine the transmit focusing that we discussed. At a specific spot, I can induce mechanical vibrations using ultrasound itself. Okay, so you use ultrasound itself to create that motion, and then you go back to the frame-based approach to observe multiple frames and then displacement and then correspondingly. So this is something known as acoustic radiation force imaging, which is really, so there's a nice journey from very trivial to motorized to ultrasound itself being used for finding the stiff tissue. Okay, so it's elastography is something which is very popular in the recent past. Now, switching back to some video mode here. So we already discussed about ultrasound creating heat in the body, right? Based on that, people have devised something known as sonothermogenetics. So you can heat up the tissue and you can use it for neuroimaging. You can actually very well. So quick, I hope you can hear the video. I mean audio also.
Precisely control your brain. By turning on and off your neural activity, you could treat brain disorders that affect billions of people around the world, like Parkinson's disease and depression. There is a new technique that might someday deliver just that. This technique is called sonothermogenetics. It is a method for controlling specific types of neurons using ultrasound.
So this is basically focusing that we discussed. So you have an array of transducers here, and you can focus literally at any point that you desire. So that's same technology they're using.
Penetrate through the human skull to target any brain regions with millimeter spatial resolution. They develop a viral construct that can deliver these.
So I'll, in the interest of time, I will pause here and then go forward. You can see the details in Chen Ultrasound Lab if you're very keen. Very interesting technology. Okay, so let's move on. So this is again 2 recent works in 2021 early. This is like a revolution. Okay, 2 people were in coma, and you can use the same technology that we discussed earlier and in the previous slide, and they were able to actually jumpstart the brain. 2 dead brains, they were able to jumpstart, and this is like magic, right? So you can imagine that where we are going. And remember, we are not opening the skull. We are talking about completely non-invasive pumping in ultrasound energy at a specific spot using focusing technology. And brain tumors also, you can do that. Then optoacoustics is another area where you are using laser to precisely guide ultrasound to a specific spot, and then use the traditional ultrasound technology to receive the reflections back. So this is something which got FDA approval, as I was telling you in the previous slide, in the recent past again. And you think that it's over? No, sound can do amazing things. I was shocked to read this. So ultrasound, MIT, not from any other university. This is reported by MIT. So you can disrupt the virus shells also. So that's something which is very interesting. But yeah, we can't believe all this until it is completely proven in clinic. But there is a potential. Now, I think this is sort of the second last slide. So we are almost at the end. So this is again taken from a very beautiful work. So can somebody guess what is it? Very difficult to guess at this point. So I'll just play this video. So this is right inside our brain. And this is not some visualization, some graphical visualization. This is captured using ultrasound at microscopic level, something known as location microscopy. So you can see here, it's a normal probe, everything technology we discussed already. So you place it. So the only issue is like skull will not penetrate ultrasound easily. So you have to identify the small gaps in the skull and allow ultrasound to go through. So the idea here actually is you will inject some micro bubbles into the brain, and then you track using the multi-frame approach that I was talking about. variations, and then you display it. So this is what happens inside our brain. So you can imagine what all things we can do if you're able to capture such activities at micrometer level precision. Okay. So if you think that that's all, no, I have something more surprising to you. Unfortunately, this may not happen in India, but it is already happening in Israel and US. Ultrasound is coming to your home. I already told a system is as low cost as even your laptop, something from Apple. So you can think of something which is coming to your home very, very soon.
Expectant mothers often worry if they don't feel fetal movement as often as they expect to. They are also prone to anxiety over their baby's development. According to statistics, there are around 210 million pregnancies every year across the world, 6.7 million in the US alone. Polsonmore has developed a mobile ultrasound scanner, which enables the mother to see the fetus whenever she feels the need. The system is comprised of a polymeric cradle with an ultrasound scanning element.
So this is the same set of array. This is using the CMUT technology that we discussed about. So you can miniaturize it and you can see the way they are arranged the array.
Embedded in the bottom. Insertion of the mobile device automatically starts the scanning. Rest the
so now you should know why you put the gel across, right?
Cradle on the mother's abdomen, and you instantly receive a clear, sharp image of the fetus. The data is immediately sent to a cloud for deep analysis, making it available for real-time inspection by the woman's obstetrician. Besides obstetrics, the Polsonmore platform enables more scanning applications for cardiology, orthopedics, and more.
Yeah, so once it comes home, you can imagine what all things we can do with it. Okay, so just it won't come to India because I don't know how many of you are aware of that. Portable ultrasound systems, not everyone can keep it because of the fetal sex determination issues. So there are some rules which prevent that. All of us cannot keep it. So we need some license to keep the machines, particularly portable ultrasound systems like this at home. So going forward, so that's it. So sort of covered everything. So we started off with the basics of ultrasound, right? We talked a lot about how the BMOD, particularly the beamforming aspect, and then the functional aspects. So we can image not only just the structure, the functional aspects inside the human body and the engineering aspects related to it. Then I just some of these technologies I try to introduce to you, something like CMUT and PMUT. If you're interested in the analog part and more in the transducer technology, this is the place to go. A lot of work can be done. Parallel processing has ever been an important area in ultrasound system, particularly when we talk about miniaturization. Okay, so it's very important the case as an engineer to play. And then newer technologies, that's always newer algorithms and that signal processing, it's extremely important to keep on evolving. And then of course, it is no more an imaging modality. It is used for a variety of applications. We saw that elastography, the therapy effects in brain, and even now, this is something which I didn't talk about. You can precisely deliver the drug at a certain point using ultrasound. So something very, very important. If you're curious, just have a search and you will find a lot of articles in this direction. Okay, so that's it from my side. Hope I was able to motivate at least some of you to go very serious in this field, otherwise, which is not very popular. And if you have any questions, we can take it now, or you can always contact me at this email address. And I have also not presented any of the stuff that we are doing in our group. We are actually trying to work in some of these fields that I mentioned, and you can find all those details in these two websites. And you can keep asking the questions now, but try to end the course with sort of a brief description of our group here. So these are the PhD scholars, and then this is what we do. So I'll keep this slide and we'll take any questions if you have. Thank you.
Thank you, Mahesh sir. So viewers, you can start asking your the queries and everything what you want. You can unmute yourself and one by one we can take on the queries.
Yeah, if you're shy, you can put in the chat also.
Yes, of course.
Hello, sir.
Yeah.
I'm Dr. Sabina. I'm a faculty in TKM Engineering College.
Yeah.
I am also from electrical department. And actually, I am working in image processing side.
Yeah.
So the clarity of the ultrasound image, are you satisfied with the diagnostic purpose, or is there any improvement needed?
Yeah, definitely. Actually, maybe let me go back to one of the images. Yeah, so that's a good question. So one of the always, I think the evergreen area in ultrasound has been actually to improve the image quality. So there's been a lot of technology which has improved maybe from 1980s to where we are now. There's a lot of things have been tried, different ways of beamforming, for example. All those things were towards the improvement in image quality. And then if you see the current images that we have in the most modern ultrasound systems, they are of much better quality than maybe even 2000 systems. So, but still, even the group that I am actually leading, we are also trying to improve the image quality, either using the signal processing way or using the image processing way. But to answer your question, yes, the image quality of an ultrasound system is not as good as, let's say, CT or an MRI system. Definitely not. And I don't think that any of the ultrasound engineers even think of mimicking an MRI or a CT system. But extra information is that people are trying to look at this point. But another, on a related note, on a interesting note, the clinicians are so used to this image quality, and they really want the images in a similar quality. If you try to denoise the image and try to improve it, they will say that you are killing my image. So that is the situation that people have reached now. They are so used to the texture. For example, here you see, if you try to smooth this and make it like one grayscale here, they will think that, oh, the texture is lost. So you are really trying to kill the information which is present already in this image. So they are sort of liking it, and those who are used to ultrasound, I think they are very serious about having this sort of a texture preserved. So they don't want really to improvise all our classical image processing techniques and try to improve upon this image. They really don't want that.
Okay, thank you, sir. And one thing is the cost wise also you are bringing it cheaper. So like compared to CT and MRI.
Correct.
That's an added advantage.
Yeah, it's always an added advantage. Not only that, actually dynamic imaging, as I said, you can move. The subject can actually move when the scanning is doing. So that's one significant advantage for ultrasound.
And really a wonderful session, sir. Thank you.
Thank you. Thank you.
Nice to know you.
Yeah, so there is one question from Fadveer actually. So Swaroop, okay. Swaroop is actually something which is Texas Instruments board. Let me go to the slide where he's referring to. So he's going this slide. So the board that you see over here is a board which is designed by Texas Instruments. A lot of companies actually, Texas Instruments, Analog Devices, then Maxim, all these companies are actually making system on chip specifically for ultrasound. So this board is manufactured by Texas Instruments and given to us for evaluation. And this is not an indigenous board, definitely not. And we all know that India is lacking a lot behind in terms of fabrication and chip manufacturing in India. Design is done in Bangalore team, but manufacturing is done outside. But yeah, probably with all the push from government, we may see something which is getting manufactured in India. All, if we can do that, a lot of the cost even comes further down.
Is it a customized one, that one?
Yeah, this is actually customized by TI. So this is something like a 64 channel front end. You can connect 64 transducers to this, or 128. I think this 128 one. Yeah, Narayanan, you had a question? Yeah, when the so the question is, when the CMUT is in vicinity to the gel or water, does that change the frequency of excitation? I think there will be some window. So if you see the CMET technology, they do have a casing which well within that is the vibration getting induced. So I doubt that will happen. Yeah, but I'm not the right person to answer that. But my intuition is, let me go to that diagram. Sorry. Yeah. So you see over here, probably there will be a casing with the acoustic lens and the other aspects. So the within that casing only this vibration will be happening. So I don't think there will be an issue. But one thing actually very important is like there is a near field to the ultrasound. So if you put the probe on the body, there is some dead zone because immediate vicinity you may not be able to image with the current technology. You may have to, let's say, some one maybe with less than 1 centimeter, maybe it will be a dead zone for us. But yeah, in this case, my intuition is it won't be. It will not happen because there will be some sufficient casing with sufficient membrane coverage so that it can vibrate and the pressing on the body will not affect the vibration.
Sir, then between the plate and that within that dead zone, the area will be full of air, right? So there will be more absorption.
No, there will be a some material filling inside, and then outside of that we will be putting the gel, right?
Okay.
Yeah, everything will be conductive medium only. Moment you have air, you have a lot of issues. In fact, you will think that air is a sort of a enemy to us. So if you think that way, I think ultrasound modality or the people working in ultrasound are the best people who are taking advantage of the issues in ultrasound. For example, the technology that I showed you here. This is actually making use of bubbles, air bubbles inside the brain. So they pump air micro bubbles into the brain and create disturbance inside the brain and using ultrasound to get it back. So people are leveraging the disadvantage to their advantage. But air is always a disadvantage for ultrasound, but you can make use of those by using technology like this.
Thank you, sir.
Yeah, I think there are no more questions. So thank you. Yeah, so maybe we can.
Thank you. Yeah. Thank you a lot. Really a wonderful session. We had basics, starting from basics of ultrasound imaging system. And the thing is that the way it has been miniaturized from 1950, we have seen that big system. And now what we are seeing it is a portable one in the form of mobile. Then he had discussed about the physics behind the ultrasound imaging system, then the engineering side, and later the advances in the diagnostics of ultrasound imaging system. So altogether, it has given a wonderful session. Like many of the participants have got the basics or insight into ultrasound imaging system. So on behalf of IEEE Malabar Subsection, I extend my wholehearted thanks for coming online and giving a wonderful session. And hope we'll have many more in future. So thank you from IEEE Malabar Subsection. I also thank all the participants who have taken their time to spend for listening this particular session. Thank you once again. Thank you, sir.
Yeah, thank you, Sabik. I think you also deserve a lot of accolades for the conduct of this seminar, and let it have 100 one coming soon. So all the best wishes for that, and thank you for your efforts. Yeah, thank you for this opportunity as well. Bye.
Thank you, sir. Thank you, Ari, for organizing.
Thank you, sir, for giving us an opportunity. Hope we can collaborate more on such events from IIT Palakkad and our student branch.
Sure, sir.
Yes,
we'll do that.
Thank you, Mahesh, sir. Thank you.
Yeah, sir. Thank you, Harry. Yeah, thank you.
Months to come, and we'll do that.
Yes, sir. Yes, sure, sir.
Thank you.
Thank you. Bye.
Thank you. Bye.
Bye.